Okay, so let us continue the discussion of the filtering effect and yeah, pretty much the same example that we have seen where when we try to do the low pass filtering using a practically realizable filter, we end up getting some distortion or some uh, disturbance in the frequency domain where we saw that the ideal shape in the frequency domain, which was this rectangular pulse, became kind of smeared out. It became spreaded out, and the amount of the spreading, the smearing, and the amount of waves that were present in the distorted version of the ideal filter depended uh, crucially on the truncation that we did in the time domain. Now, uh, we take another example now in which let us say that the transmitter is sending out some signal, some continuous time signal, some s of t, and the receiver is getting the signal after it passes through some communication channel. Now, so far in the class, we have taken the communication channel to be pretty simple. All that it does is it either it flips the bits or it introduces Gaussian noise. But other than that, we haven't done any more detailed modeling of the real world communication channels. So, one slightly more detailed representation of the effect of a communication channel, it can be either a wireless channel, the channel that your cell phone signal sees as it gets transmitted out from either the base station towards your cell phone or from your cell phone towards the base station. So it can be either a wireless channel or it can even be a wireline channel. If you have a landline phone at your home, then the cable itself becomes a communication channel, and that cable will have certain type of uh, frequency response. In a lot of such cases, the communication channel itself can be modeled as an LTI or LSI system. And correspondingly, we will associate some impulse response and some corresponding frequency response to such a wireless or wireline, in general, any communication system. So now what happens is if we model this communication channel as uh, itself as an LSI system, LTI system, then the signal that we are sending from the transmitter, it effectively passes through this LSI system, and so what comes out, the received signal, in time domain is a convolution of the impulse response of this communication channel with the transmitted signal. If or equivalently in frequency domain, we get the multiplication of capital H of f with capital S of f. Okay, now depending on the shape of capital H of f, or more specifically, depending on the relative shapes of H of f and S of f, the difference in the shapes of H of f and S of f, the transmitted signal spectrum and the frequency response capital H of f of the channel, depending on that, R of f will either be very similar to capital S of f or it may not be similar to S of f. Essentially, this capital H of f itself may act like a gate, it may act like a filter, and the signal will pass through this gate, this communication channel, properly only if the gate is wide enough to allow the entire width of S of f to go through. If it is not wide enough, and that is why I said it is the relative part which matters. Relative to the width of capital S of f, if capital H of f is not wide, then the entire spectrum of S of f will not get through the communication channel. And therefore, what we will get at the receiver this capital R of f, will be a spectrum which will be a distorted version of capital S of f. And whenever we distort the signal in frequency domain, obviously the time domain will also take a hit. So that is something that is quite common in the design of a communication system. This is something that we have to keep in mind. So again, let us take some examples of this particular observation. And what I am doing here in this example is a very simple thing. I'm taking this rectangular pulses. They are this periodic rectangular pulses that we have already seen earlier. Actually, if you recall, you have seen this rectangular signal. It's a periodic signal, and it is that signal which I am passing through a communication channel. This gray colored rectangular signal is the input to the channel, and therefore the Fourier transform of the input is same as what is shown here. Okay, so it has a sink shape, and the width of the sink shape depends on the width of this gray colored pulses, and the separation between the blue colored samples depends on the periodicity of the gray colored rectangular pulses which is at the input. Now, in this particular example, what I said is that my communication channel is wide. The width of h of f goes from minus 450 to plus 450. So you can see that it will let almost all of the signal pass through. You might see some shaded out portion at the very end. The communication channel, this h of f, is not letting those parts go through, and so they get blanked out. And therefore, at the receiver, instead of getting a nice rectangular pulse shown in the gray, I get a smeared out version, almost exactly like the Gibbs phenomenon. Because here in the frequency domain, I have truncated the, the Fourier transform. So when the receiver gets this blue colored signal, it will see that there is a lot of ripple to it, and then there is some shape which otherwise looks a lot like a rectangular waveform which is actually sent by the transmitter. But now if I say that the channel, the communication channel is a bit more stringent, so that it doesn't let uh, the signal component above minus 350 hertz to plus 350 hertz pass through. So now you see a lot of this original signal spectrum got zeroed out by the channel, by this option here. And so just like as in Gibbs phenomenon, now at the receiver I see more ripples. Basically, the signal is getting distorted by the communication channel in the frequency domain, and therefore in the time domain what the receiver gets is not ideal periodic rectangular pulses, but it sees some distorted version of that. As I keep on making the channel response tighter and tighter, those ripples become sharper and ripples become wider and wider, and now I end up getting something which doesn't look a lot like rectangular pulses anymore. So this is one more demonstration by which we see that um, the filtering can have some side effects. Typically, the filtering is good. Typically, filtering is in our control. We implement a filter at our receiver in our own hardware or software in order to get rid of the noise, the out of band noise, as we saw with that example of a bird chirping. What this example shows is that filtering is prevalent. It may not be entirely in your control. In this case, the filtering was being kind of implemented by the nature, by the nature of the communication channel itself. The way the signal is getting transmitted, the way it is passing through the wireless channel, the electromagnetic energy, the way it is propagating through the either the cables or through a wireless medium, that itself acts sort of like a filter which removes some high frequency component in this example, and because of that the output of the channel at the receiver may be a significantly distorted version of the input. So that is kind of a negative side effect or negative effect, an example of a negative effect of filtering. Okay, so that is pretty much it on terms of the filtering aspect. Um, Before we conclude this entire topic, let us consider a few other properties of the Fourier transform. Um, okay, so there is one very subtle property, very elegant property, which we haven't spent a whole lot of time on. But uh, in case if you end up working on this transform domain relationships, this is something that is very useful to keep in mind. And again, there are some very powerful applications that you can draw out of this property, which says that if the signal is symmetric in one domain, in the other domain it becomes real valued. So for example, if I am having a time domain signal which is symmetric around t equal to 0, meaning that if I take t equal to 0 times 0 as the axis, the vertical axis, y axis at t equal to 0, and if I look on the positive side of that, on the right hand side, basically t greater than 0, if the shape of the signal is same as how it looks like for t in less than 0, this is called mirror symmetry. So if I fold the waveform of the signal um, at the y-axis for t equal to 0, and if they both folded out shapes kind of land on top of each other, then it is called symmetric in time domain. What are the examples of a symmetric signal? Well, let us see. This is a symmetric signal. You can see this is for t equal to 0. How the signal looks like on negative t is same as how it looks like on the positive t. So this is a symmetric signal in time domain. This rectangular pulse is also symmetric, but now it is symmetric in frequency domain. Its shape around f equal to 0 is identical on both the sides of this axis. If I draw a triangular function around 0 and having the same width around 0 on the positive and the negative sides, then even the triangular pulse also will be a symmetric pulse. What will not be a symmetric pulse? Well, if I take this sinc function and if I shift it so that instead of being centered at 0, it is centered at 10, then that is not a symmetric signal anymore, because around t equal to 0, the symmetry is lost. There is far more energy on the positive time side compared to the negative time side, because simply because I have shifted the sinc function uh, on the right hand I've shifted it to the right. So there's this property of Fourier transform which says that if the signal is symmetric in one domain, let us say in one case it is symmetric in time domain, then its Fourier transform, its frequency domain representation is going to be entirely real valued. What is an example of that? Well, the cosine signal, cosine of 2 pi f c of t, is one such signal which is symmetric around t equal to 0. You can see that. You can draw a cosine function as a function of t, cosine of 2 pi f c t. If you draw it as a function of t, you will see that it has this mirror image symmetry around t equal to 0. Then take the Fourier transform of cosine of 2 pi f c t. That would be quite similar to what we have done already for the sine function. Remember one of the examples that we did earlier where we took the Fourier transform of sine function. You follow the same methodology. You will get the Fourier transform of a cosine 2 pi f c of t, and you will see that that Fourier transform will be real valued. So that is one property. The second property is something that we have actually already looked at, which says that a shift in one domain results in complex phase modulation in the other domain. Um, and so here, the second property is actually just a repeat of what we have already studied. Let us look at it very quickly and we will be able to move on. Shift in time domain translates to complex phase modulation in the frequency domain, or shift in frequency domain represented by this expression over here translates to complex phase modulation in the time domain. So this second property that we were just now looking at is something that we have already familiarized ourselves with. But let us consider maybe one or two examples of this shift property or the complex modulation property. If you recall, when we were talking about converting the ideal low pass filter to the practical low pass filter, we were saying that there are two problems. And we have talked about only one problem, which was that the length was infinity. But there is one more problem, one other problem, which is that such a filter, even if it is finite in length, even if we make h of n to be finite in length, still the system is not practically realizable because it belongs to a class of systems which is called non-causal systems. What is a non-causal system? Any system whose impulse response is non-zero for n less than 0 is not causal. And we cannot have a non-causal system. Why not? Well, impulse response h of n of a linear shift invariant system is the output of the system when we apply a delta function as the input. You go back to our earlier lectures and you will see that this was the way we have defined h of n. Now, delta function delta of n is an impulse at n equal to 0. So, what it means is that we are exciting the system, we are giving an input to the system at n equal to 0. And that is the only time we are giving the input. We are not giving the input before n equal to 0 and we are not giving any input after n equal to 0. So if we are exciting the system, if we are kind of probing the system at n equal to 0, how can it produce output for n values which are less than 0? It cannot. It means if h of n is non-zero for n less than 0, what it means is that even before applying the input, the system knew that now at n equal to 0, I'm going to get an input, and so I better start producing the output. So, such a system is not practically realizable. It is not a causal system. Causal system Causal systems are those which follow the cause and the effect relationship. If you observe an effect, that is always due to some cause. You can't observe an effect if the cause is not present. Um, if suppose somebody pulls your hand and your hand starts hurting, then the effect that your hand is giving you pain has happened only after somebody pulled your hand. A non causal behavior would be that your hand starts hurting even before somebody pulled it or twisted it. How does your hand know that it is going to get twisted at n equal to 0, so I better start hurting at n equal to -5 or -10? Such a system is anti-causal or non-causal. And we do not want to have any practical system which is non-causal. Mathematically, it is fine. If you are just doing a mathematical understanding, conceptual understanding, it is fine. But for practical realization, this is the second problem of this ideal low pass filter, that it is a non-causal system. Why it is non-causal? Because this h of n, or even in this case, truncated h of n, ht of n, is defined for values of n less than 0. In a way, this is good because n is defined for n less than 0. This ht of n is symmetric function of n, and therefore its Fourier transform is real valued. I get this blue colored frequency response, which is all there is to it. This is not partial Fourier transform. There is no imaginary component, or if I'm considering this as magnitude, that is it. There is no phase. This is real valued. The reason it is real valued is because of that first property. This ht of n is symmetric. But what we have said is that in a practical system, this cannot be the case. A practical system would be the one where we would take this ht of n and we will move it by capital N divided by 2 samples, so that this very first sample which is becoming non-zero, it shifts to n equal to 0. This entire pulse we would have to shift it so that for all values of n -1 and less, ht of n is entirely 0. We would have to just simply shift it, slide this pulse rightward, so that the very first non-zero sample occurs earliest at n equal to 0. So the second problem, that the system is non-causal, can be solved by applying a time shift of capital N samples to the truncated filter impulse response. And after the time shift, this system will be practical. It will have finite length because we truncated it, and it will be causal because we shifted it in time. However, because we shifted it in time, according to the first property, because the system is no longer symmetric, we should not expect the frequency response, capital H of f, to be real valued anymore. But that indeed is the case. If you see this equation that we had written, if I have certain signal and if I shift it in time domain, my original spectrum x of f, which was real valued, remember before time shift, the impulse response h t of n was symmetric. Therefore, capital X of f was, or capital H of f was real valued. But after I introduce a time shift so as to make the filter causal, now the Fourier transform will not be real valued, it will have this additional complex valued term, which is a function of how much time shift I have introduced. Okay, so that this kind of shows uh, two things at once. It gives us the application of the very first property, which is that if we disturb the symmetry in the time domain in order to make, or in order to turn an anti-causal system into a causal system, our frequency response is going to become complex valued instead of real valued. And that is exactly the second property, that a shift in one domain results in complex phase modulation. So you see in this case, property 1 and property 2 both are getting kind of applied in this process of turning the system or the filter into a causal system or a causal filter. Now, the other application of this shift property of Fourier transform is that we have considered the ideal low pass filter. Remember, it is in frequency domain, it is a rectangular function um, centered at small f equal to 0, and it has a width uh, which depends on uh, the, the width of our desired signal. What if we want to turn this low pass filter which passes the low frequencies, what if we want to turn it into a high pass filter? Remember, the low pass filter is like this. It is centered at 0 and it has a certain width around 0. So it passes all the low frequencies and and it rejects all the high frequencies. In this discrete time case, what is the highest frequency? Remember, it is plus zero point 0.5 and minus zero point 0.5. These are the highest frequencies. The smallest frequency is 0. And remember, this is a periodic signal because my time domain is discretized, meaning that I'm showing only the fundamental period. Actually, in the frequency domain, this is going to keep on repeating every 1 unit apart. 0, 1, minus 1, plus 2, minus 2, and so on. It will look exactly the same. So now if I suppose want to turn this filter, which is low pass filter, because it passes only the low frequency and it rejects all the high frequencies, if I want to turn it into a high pass filter instead, then you can see that I will have to shift this rectangular pulse, which is centered at 0, I will have to shift it by half unit in this normalized frequency. So instead of being centered at 0, it will be centered at zero point 0.5. But a shift in frequency domain is going to cause the time domain to get modulated. How it is going to get modulated is the last thing that we are going to look at. So we shift the ideal low pass filter by f equal to zero point 0.5, and the result is an ideal high pass filter. It will pass all the frequencies around zero point 0.5 and then it will reject all the low valued frequencies. So small f is 1/2, and we need to multiply our time domain impulse response, which is the sinc function. Remember, we will need to multiply it by e to the power j 2 pi fn. If I plug f equal to 1/2, I get e to the power j pi n. N is the index of time, and it varies from minus infinity to positive infinity, and therefore as I keep on incrementing n, what I get is just simply 1 minus 1, 1 minus 1, 1 minus 1. So quite surprisingly, if I take this sinc function over here, and if I just flip the sign of all uh, odd valued n index samples, so whenever it is positive, I make it negative. Whenever it is negative, I make it positive. Then, in fact, what I will end up getting is a high pass filter, quite surprisingly. So that is kind of yet another application of this property. And now that we are talking about the LSI systems, I thought that we'll conclude this topic by summarizing the properties of the linear shift invariant systems. And so last two slides of this topic are on that. Um, in general, let us look at why it is called linear shift invariant system. In fact, we will not be talking about the reason why it is called shift invariant system in great depth. What I can say is that the impulse response h of n um, does not change if instead of exciting the filter with an impulse at n equal to 0, if you excite it at n equal to 5, you will get the same impulse response which gets shifted by 5 samples. Basically, the impulse response is not dependent on time index. That is why it is called shift invariant. But why is it called linear? Well, suppose if we have some function f, it takes input x and it produces output y. Then for what type of functions this will hold? That if you have input as x1 plus x2, the output is y1 plus y2. Well, what if y is equal to x squared? Then if I do x1 plus x2 squared, I'm not going to get x1 squared plus x2 squared. I'm not going to get y1 plus y2. I'm going to have this cross product term also. And so this is a non-linear system. And it makes sense. Y equal to x squared is not a linear function. What about y equal to mx plus c? You will say that now this is a linear function. It's pretty much the equation of a line, which is passing through y-axis at value of c, coordinate c. But technically, even this equation also does not follow this requirement that f of x1 plus x2 should be f of x1 plus f of x2. And you can see that very easily. If I plug in x1 plus x2 in this equation, I get fx1 plus fx2 minus c. So technically, even this line also is not a linear function for which this relationship holds. But if y is equal to fx, mx, m times x, meaning it's a line passing through the origin, then now finally we have this equality satisfied. So a linear system is the one for which if I have two inputs x1 and x2, and if I make another input which is the summation of the two, and now if I pass this x of n, which is x1n plus x2n, if I pass it through this linear system, then what I will get is an output which is the output which I would have obtained by sending this individual two inputs separately. And for the convolution operation, this property holds. You can verify that. You can just work out the math. You know the equation for the convolution. And if you work out the math, you will see that this property holds. So a linear shift invariant system is the one for which uh, the analogy is of a line passing through the origin. The other way to look at it is that, remember, we had said that the convolution operation can be represented as a matrix vector product, y is equal to h times x, where a capital H is the Toplitz's matrix and x is a vector of input samples. Well, y equal to capital H times x looks a lot like y equal to mx. And so that is why this convolution operation, or a system which implements convolution operation, is called a linear system. And these are some of the other properties of a linear shift invariant system, that you can interchange the role of input and the system impulse response. You will get the identical output y of n. You can take an input and pass it through two different systems and then add the output of those two systems, and the output that you will get will be identical to what you would have gotten if you took the input and passed it through a system whose impulse response is the sum of these two impulse response. This is kind of same as this property here, except here we were adding the input and then passing the added input through the system. In the second property, we are adding the system impulse responses instead of adding the inputs. And then finally, if I have a cascade of two systems, if I have two systems h1 of n and h2 of n back to back, instead of sending x of n through these two systems one after another, actually I can first make up a combined system which is the convolution of h1 and h2, and then pass x of n through this combined system to get y of n. And in both the cases, the green and the blue y of n remain identical. This y of n is same as this y of n, this is same as this, and so on. So these are the several properties: commutative, distributive, and associative property of the LSI systems. And with that, we conclude this topic of Fourier transformation. And this is your homework from 8th edition of Couch's book. Um, you look at all of these items that I have identified. Especially look at these properties of Fourier transformation. Work out these examples 2.3 all the way up to essentially up to 2-10. Also look at this example 214, and then just go over this section 2-6. Upamanyu Madho's book, which is available online, is also a great textbook. I would like you to focus on pages 28 to 44, and then also pages 46 to 57. And these are some of the end of the chapter problems. There are about, I don't know, maybe 30 or 35 of them that I have identified that you should try to work on. Some of these problems will be pretty hard, and so it is okay if you kind of are not able to solve each and every one of these Madhu's books questions, but at least give them a shot. At least develop some thinking. Maybe you may not be able to get the final answer, but at least start appreciating the problems as much as you can. Okay, so with that, we will conclude this topic of Fourier transformation. Um, and then we will then now have a few sessions on the one session we will spend on quantization, which, as you may recall, is this block here. We have done the sampling block in a great amount of detail. We went over the effect of sampling in time domain, how it causes periodicity in frequency domain, and so on. We also looked at the sampling theorem, that you can take a time domain signal of bandwidth b, and if you sample it at a sample rate which is greater than b, then you are going to be able to recover the original continuous time signal entirely from its samples. So we have done a detailed explanation of this sampling block. We will spend some time on this quantization block, and then we will spend some time on the modulation and demodulation. So this quantization and modulation, these two blocks are still remaining. Um, we will have some attention paid to these two different blocks in the upcoming weeks.